Yeah, hi and welcome back everyone. Thanks for getting up early on a Friday. So the last example of a dark matter production mechanism from the thermal bath or from a thermal distribution that I want to discuss is simp dark matter. Yeah, and it's not really from a thermal bath in some sense, because if you have these kind of interactions, the whole point is that dark matter can self-equilibrate. Yeah, we don't actually need a thermal bath. Yeah, so it's a sort of borderline case. Yeah, we don't need standard model interactions, at first sight at least. I will get back to this. Yeah, so then we can estimate what is needed in equilibrium. And of course, equilibrium means that both directions happen at the same rate. So that means that this direction here is a rate, well, we have two dark matter particles in equilibrium, and that will be multiplied by the production cross-section. So this direction here, that should happen at the same rate. Yeah, there we have three particles in the initial state. So it must be something that is proportional to the number density cubed. And, well, times the probability for this to happen. Yeah, and this is not really a cross-section. Yeah, in the end, you want to make sure that you actually compute the rate from the collision integral. Yeah, but you can call this object sigma v squared. Yeah, it's a pretty bad name, but it's the standard name used in the literature. Yeah, so it's not a cross-section. It doesn't have the dimensions of a cross-section. Okay. So we want to have basically detailed balance. Yeah, so these things should be able. So it should be the same. Should have the same dimensions and be equal in equilibrium. But in order to get the dimensions of this one, we can directly compare to that. Yeah? So we know that the dimension of sigma v squared must be, well, basically the dimension of a cross-section, yeah, divided by the dimension of a number density. Yeah, so that means that this is actually a dimension -5 object. Yeah, so that means we can parameterize this as, well, some coupling strength, and you have 3 external legs, so it makes sense to introduce some effective coupling to the 3rd power, and then the dark matter mass to the 5th power. You know, in the same way as we introduced some effective parameterization for the cross-section here. Okay, so then what happens outside equilibrium? So what is the Boltzmann equation for this? We could, of course, go through the entire process that we did for the other cases, but by now we basically know how to estimate these things at least. Yeah, so using detailed balance, we know that the in equilibrium, these two rates should be the same. Yeah, outside equilibrium, yeah, we have some number density, some rate in that direction. Yeah, but then we can rewrite this in terms of the equilibrium distribution for the other direction. Yeah, just because we know that in equilibrium this must be the same, and we want to get the correct scaling with the number density of the initial states, yeah, for that direction. So that means, in this case, our number density, or our Boltzmann equation, takes this form. reflecting that we have a 3-to-2 rather than a 2-to-2 process. Yes? No. Like this. Thank you. Yeah. Okay, so this is the Boltzmann equation for the number density that governs this process and describes how dark matter would self-equilibrize, bring itself into chemical equilibrium, just due to these 3-to-2 interactions. So we can then, as usual, estimate when freeze-out happens. Yeah, so freeze-out happens when the Hubble expansion rate takes over this term. So that means Hn will be roughly the same as n cubed. Yeah, and for this one, we use our parameterization here. And, well, then we do what, yes? N cubed, and there's an n cubed as well. So n squared times n e cubed. So this time I got it correct. Don't try to trick me. I was just about to add another, okay. Yeah, but, well, it's early morning and thanks for paying attention. Okay, so now we do the same estimate that we did also for the other cases. Yeah, so that means that we write the Hubble rate at freeze-out just in terms of the temperature squared, temperature squared by Planck mass, and then we know that our number density at freeze-out is given by, well, the energy density divided by the mass. Yeah, but then this redshifts just with the expansion of the universe because we don't have any interactions anymore. So we can express this as the number density at equilibrium times the redshift factor. Yeah, and then we want to make sure that this is actually the correct dark matter abundance, meaning that at equilibrium the energy density in the dark matter thus produced should be the same as the radiation density. Radiation density we can write as TeQ to the fourth power. So that means that here we have TeQ, Tf squared, and then times Tf over m, where this is this factor x, or 1 over x. Yeah, it's essentially order unity, which is not quite right, but for the purpose of our estimate, it's a factor of order unity. Actually, freeze-out happens slightly earlier than in the WIMP case, the 2-to-2 case, because we need higher energies for 2-to-3 processes to be possible. We need to have enough energy to create rest mass. Okay, so then you just plug this in, solve for alpha, or mass, or the mass, and you find that the relation between these two is like this. Yeah, so remember that for 2-to-2 freeze-out, there was just a factor of 1 here and a square root here. So there we had with the geometric mean of Planck mass and temperature at equality. Yeah, here we have some kind of a generalized geometric mean. So for example, we can put this effective coupling to 1, and then this gives 100 MeV. So this is the scale of strong interactions. And for that reason, this has been referred to as a strong or a simp miracle sometimes. Yeah, so just as in the WIMP case, we were somehow led to the conclusion that there is a reference to the weak scale, which we didn't put into our problem. Yeah, we start with some interaction. We want to solve the observe or the dark matter problem, that is, explain the observed dark matter abundance, and then we are led to the electroweak scale. Here we are led to the strong scale. Yeah, now, of course, I mean, you should take this with a huge grain of salt, because, well, in the WIMP case, first of all, I argued that, just as the case here, yeah, we actually only fix the ratio of mass and coupling constant. Yeah, so in the WIMP case, like one of the options is to have everything at the electroweak scale. Yeah, but that is actually a very nice option because there's independent physics evidence that we want to change or do something at the electroweak scales. Yeah, there's something to be understood. The same cannot necessarily be said about the strong scale, so it's not as compelling if you wish. The other point is that, well, just from seeing all these miracles, yeah, you should get suspicious. Yeah, so, I mean, if there's a miracle everywhere, maybe there isn't any miracle at all. Yeah, and that's also a point here. Yeah, and indeed, you can do exactly the same calculation here, the same estimate, yeah, and see that my point about a generalized geometric mean actually generalizes in the sense that if we add many particles here, so instead of a 2 to 3, we have a 2 to n process. Yeah, this actually just goes to an n minus 1 and this one to an n. Yeah, so it's a fully generalized geometric mean. And you wouldn't, I mean, happily declare a miracle for each value of n. Yeah, so that's something to keep in mind. Okay, but there's actually something we need to take into account that is different from the 2 to 2 freeze out, namely that these 3 to 2 interactions, yeah, the annihilations, actually heat up the dark matter bath, yeah, because we convert rest mass to energy. And we need to do something about this. Yeah, so we have basically two options. The first one is that we just add an additional interaction now with the standard model heat bath, and in that sense, this discussion here belongs to the class of dark matter production from the thermal bath. Yeah, so we have a standard WIMP-like interaction of this type that keeps the dark matter particles in kinetic equilibrium with the heat bath. And then we can parameterize this cross-section as usual. Yeah, so we have constant scatterings. They are not strong enough to chemically equilibrize the dark matter particles. Otherwise, we would have just have the ordinary WIMP freeze out. But they keep it at the same temperature. And of course, this is actually sort of the kind of process that I implicitly assumed in this estimate. Yeah, because I only referred to one temperature here, which is the heat bath temperature. So this cools dark matter to the standard model or heat bath temperature. The other option is that we have a completely secluded dark matter. Yeah, and that is close to what was also discussed in one of the short talks yesterday evening. Yeah, so basically, it means that, well, dark matter cannibalizes and, well, keeps itself warm by doing so. Yeah, so it converts rest mass to kinetic energy. So how can we understand the effect? Well, in equilibrium, yeah, we have basically, well, equilibrium means equilibrium in the heat bath and equilibrium in this completely secluded dark sector. So that means that entropy is conserved separately in the two sectors. So we've conserved entropy, in particular in the dark sector alone. So the entropy density is always the energy density plus pressure by, well, now the dark sector temperature, Tk. Since we are already in the non-relativistic regime, even if that's only mildly the case, we can neglect the pressure. So this is essentially given by the Boltzmann suppression. And, well, since entropy is conserved, this is entropy density. This must scale like T cubed. Sorry, like a to the minus 3. Yeah, so as the universe expands. Okay, so we solve for Tq, T chi. It goes like 1 over the logarithm of T. Yeah, A scales like 1 over T. Now T is the standard model temperature. So in other words, the temperature will grow very fast in the dark sector. And that's also something that was pointed out already yesterday. So that is generically a problem, because if we have a very hot dark sector, it means that the dark matter particles are moving way too fast in order to be compatible with structure formation. Yeah, so we need to avoid that, and we do so, or the only way of doing that is to start with a dark matter abundance. Yeah, that is very small. So then when it equilibrizes, the entropy density in the dark sector is much smaller than the entropy density in the standard model. Yeah.
So this result is only valid for sublimited dark sector?
Yes, exactly. Because as I just pointed out, this is what we need anyway. Yeah, and in fact, I mean, what are the numbers? So for example, if you have a 10 MeV, yeah, so just a bit below this estimate here, 10 MeV dark matter particle, yeah, in order to avoid structure formation bounds, you need to have a dark sector entropy density, yeah, that you start with, that is a factor of 10 to the 5 smaller than the one in the standard model. Yeah, so this kind of model is less appealing in this sense that you somehow need an additional input, also, an add-on to the model that explains why you start with having a secluded dark sector is fine, but typically when you talk about a secluded dark sector, you have in mind that at very high temperatures, typically there is some kind of portal. Yeah, you can't forbid portals to the standard model, like there are some dimension 4 operators that actually connect to dark sectors. So you would expect that at very high temperatures, the two sectors are in equilibrium anyway. Yeah, so you need to explicitly avoid that somehow. And then, for example, say that the inflaton directly populates the dark sector and the standard model sector completely separately. So you need to break some invariances there, some symmetries. Okay, so how can we summarize this picture? We can do a little phase diagram again with this coupling alpha psi here, 2-to-2 coupling, and our dark matter mass. Put this in GeV, and then I do some numbers here just to give you a sense of scale. And here we have 10 to the minus 4 GeV, and here 1 in this plot. Yeah, so for a line that looks roughly like that, we have a cooling rate due to this process that is smaller than the 3-to-2 rate. Yeah, so this is this case B. Yeah, so this is cannibal dark matter. Then for very large couplings, yeah, of this type, we actually back to the WIMP case. So there, this annihilation rate is larger than the 3-to-2 rate. Yeah, and then, okay, so I say annihilation rate here, I introduced it as a scattering rate, but of course you can just turn around the diagram for a parameterization like that. That means that here, 2-to-2 interactions are more relevant than 3-to-2 interactions. So here we have ordinary WIMPs. And in this region, this is the SIMP parameter range. Yeah, this connects the different types of dark matter production from the heat bath that we've discussed. Okay, just in case you wonder why the couplings are so small, yeah, I told you something else. For WIMPs, we need larger couplings. That's because we have a much smaller mass scale than the electroweak scale. The number? 10 to the minus 8. Yeah, sorry. Yeah, so this is at 0.1 MeV. Yeah, so remember that to freeze out just fixes the ratio of coupling to mass and not the scale independently. Okay. Any questions about SIMPs or dark matter production from the thermal bath in general? Okay, if not, we move on to discussing something conceptually very different. Yeah, so now we move away from talking about collision operators, heat bath, and the like, and think about really different ways of producing dark matter. So this is fully non-thermal production. And well, in order to sort of introduce the discussion here, it's interesting to address a question that I haven't addressed explicitly so far. Namely, how light can dark matter be? Yeah, and I want to do that here because what I'm talking about here is mostly relevant in some sense for very light dark matter. Yeah, with the exception of black holes, which I might say very little about at the end. Okay, so for the thermal production that we've discussed, yeah, I said that if dark matter is lighter than MeV or so, yeah, then we have a cosmological problem. Yeah, so why is that? Well, if it's lighter than an MeV or so, it means that it's relativistic at MeV temperatures. MeV should ring a bell. That's when nucleosynthesis happens. Yeah, there we have basically precision measurements. Yeah, and this is basically not allowed anymore. Yeah, so even if there's only a single degree of freedom, an additional relativistic degree of freedom, it will increase the Hubble rate during BBN, because the Hubble rate is proportional to the energy density. Energy density is temperature to the fourth times the number of degrees of freedom. Yeah, so if you add 1 degree of freedom compared to the order 10 degrees of freedom that we have in the standard model at these temperatures, you actually increase the Hubble rate by 10%. And that's not consistent with observations. So this is excluded by BBN. Yeah, but the way I describe this only applies to a specific case, namely only if dark matter is fully thermalized. Yeah, so it's not a bound that applies for freeze-end production, for example. Okay, so then if we go to lighter scales, if we have dark matter lighter than a few keV, this is also something that I mentioned in passing, then the dark matter particles produced from the thermal bath are simply moving too fast. So that means they free stream out of underdense regions, small regions, suppressing structure formation at small scales, and that is excluded. So it is excluded by structure formation. For dark matter produced from the standard model thermal bath. Note the way this is formulated here. It's produced from the thermal bath, but doesn't have to be fully thermalized in order for this constraint to apply. And it's the standard model thermal bath. If we have dark matter production from a secluded sector dark bath, which could be at a smaller temperature, the inherited velocity dispersion of the dark matter particles would be smaller, and you can invade these bounds, meaning that you could have smaller masses. Okay, if we go down to even smaller or only slightly smaller masses, then it turns out that there's a completely independent, a bound that is completely independent of the production mechanism, which applies to fermions just because of Pauli pressure, or the Pauli exclusion principle. So it turns out that you have fermions that are lighter than a keV or so. It's just not possible to squeeze sufficiently dark matter inside a dwarf galaxy without violating the Pauli exclusion principle. That's completely independent of the production mechanism. So this is the phase space degeneracy. Dwarf spheroidals. For fermionic dark matter. This goes under the name of Tremaine gun bound. Okay. So then, what about bosonic dark matter? Scalars, vectors. Those are almost unconstrained. By almost, I mean unconstrained with respect to these kind of scales. If you go to really extremely light masses, 10 to the minus 22 electron volts, or 21, the most recent bounds, then it turns out that even for bosonic particles, the de Broglie wavelength of these particles is actually larger than, again, the scale of dwarf spheroidals. So again, it's not possible to build any structures that are smaller than that. Okay, so but what does that actually mean? So if we have very light dark matter, it means that we have very large number densities, because what we measure observationally is the energy density, the mass density. And that in turn means that these light dark matter particles, at some point the description of this kind of situation as a particle just breaks down. You have so high occupation numbers that this is a field rather than a particle. So just to give you a sense of numbers, the number of CMB photons, that's something that you probably remember from Yvonne's lecture, is roughly 400 per cubic centimeter. And, well, how many dark matter particles do we have? We want to make sure that we match the observed density. So that corresponds cosmologically to about 1 particle per keV, 1 particle per centimeter cubed for keV dark matter. Yeah. Correspondingly, if you go to very light dark matter, even 10 to the minus 20 electron volts are allowed, these dark matter particles would be way more abundant than CMB photons. So note that this is the average cosmological number density, which is of course much smaller than the local dark matter density. So the local dark matter density is more like a GeV per cubic centimeter. So a factor of 10 to the 6 higher than the average cosmological number density. Okay, so let me very briefly mention the most commonly discussed mechanism to produce these kind of candidates, and that's the misalignment mechanism. You will discuss this in more detail next week, but let me just very briefly sketch what the idea is. So, as argued here, you want to describe a field rather than a particle, meaning that we really should adopt the field theory description. We have a Lagrangian, and then from that you derive the equation of motions, that is the Clay-Gordon equation. And you evaluate the D'Alembert operator in the relevant background, so Friedmann, Robertson, Walker. So if you do that, you get an equation like that. Gradient term. And, well, first of all, so when you properly discuss this, these terms are actually phenomenologically relevant, but at 0 level, they are not. Why is that? Because these gradient terms here, and when you go to Fourier space, this is just describes just the wave number, k squared. And then you have the a to the minus 2 here. So any perturbation, any spatial perturbation, just decays away very quickly. So it's not relevant for the overall evolution of the energy density. Okay, so how does the misalignment mechanism work? Well, basically, you have a situation where the potential here evolves as a function of temperature. So at early times, we have a situation where, yes? No, it's a V prime, very sorry. It's too early also for me. And you deserve an extra coffee for paying attention. Okay, so at early times, high temperatures, we don't have an appreciable potential, or not a derivative, meaning that we are in the minimum of some potential or no potential at all. So that means that we have some kind of slow roll condition where this term dominates over that one. So that means that phi double dot plus 3 a dot over a phi dot is 0. And then, well, you can actually easily solve that equation, namely that phi dot must scale like h to the minus 3. Yeah, what does that mean? That, well, even if you start with an initial velocity in the field, if the field is moving, yeah, this will redshift very, very quickly. So the field will be at rest, just a constant, very soon, independent of the initial conditions. Yeah, and that's an important parameter for axion or Alp-like phenomenology, this initial field value phi I. Yeah, we can't know that beforehand, so it's basically an input parameter. Then at later times, yeah, below some critical temperature, we have some kind of phase transition, or for other reasons the potential becomes relevant. And what you typically do, or in the context of the misalignment mechanism, what you essentially need is that you have a slowly varying potential, yeah, where the slope of the potentials varies slowly. So my V prime is a derivative with respect to the field here, and what I mean by slowly varying is that it varies slowly as a function of cosmic time or temperature. Yeah, so then it means that the field will, it's also non-zero importantly, yeah, so that means that the field starts to oscillate in the potential around the minimum, and on top of that the potential can vary slowly. Yeah, and then you can describe that situation. Well, let's first write that down. So field starts to oscillate around the minimum. Yeah, and you can describe this, you can solve the field equation basically by a WKB ansatz, because of this assumption. Yeah, so that means that you write the field as follows. Yeah, so you have an oscillation and some time-dependent amplitude, and this one is slowly changing, and this describes the fast oscillations. Yeah, that's the standard WKB ansatz. Yeah, then you can solve the field equations, and I skipped the details here, for a very general parameterization. Yeah, and the point is, somewhat surprisingly, that, well, of course, if you solve the field equation, you get the time evolution of phi. Yeah, if you have the time evolution of phi, you can plug that into the stress energy tensor for phi, yeah, meaning that you can compute the pressure and the energy density of the field. Yeah, and then, surprisingly, you will find that the average energy density scales like h to the minus 3, and the average pressure is much smaller than the average density. In other words, this field, which is fastly oscillating, behaves from a global point of view exactly like CDM. Yeah, it's conceptually something completely different, but cosmologically it just looks like that. Yeah, so this is just at the background level, so you also have to make sure that perturbations work out, yeah, and that is when this term here becomes relevant. Yeah, and this is what you will probably hear more about next week. So the result is still the same, that even though we have a fundamentally different description, yeah, from a cosmological point of view, this just behaves like vanilla CDM. Any questions? Okay. So I was on purpose short here, such that we have a little bit more time to talk about yet something completely different, namely gravitational production. But I think we take a short break before that, and then start with after a coffee. Yet another completely different mechanism, that doesn't require any of the language that I've been using so far. And that is basically asking, or one way to motivate this is asking the somewhat depressing question, okay, we measure dark matter, we measure its gravitational impact. Is there a way to explain the existence of the observed abundance and still having virtually no interactions with anything that we could see? And the answer, unfortunately, is yes. So the simplest way is that the inflaton could, for example, directly decay to dark matter particles that don't interact with anything else. This is a bit ad hoc. It's a academic possibility, yes. But more interesting is the point that if you have something that is really completely secluded, where you don't have to argue why you, for example, have completely different couplings between standard model and dark matter particles, but just no coupling at all. Something that has actually no interactions with ordinary matter. And this happens then, I mean, of course, what you can't switch off is gravity. Gravity is always there. And it turns out that you can produce dark matter even only through gravity in sufficient amounts. This would typically happen at the end of inflation. So in order to understand this, I should probably have a brief recap of QFT and curved spacetime. I guess not everyone has seen this. Who has not seen? Yeah, okay, good. So, first of all, in GR, recall the minimal coupling principle, which basically means that we can construct or fully take into account the effect of gravity by starting from our Lorentz invariant theory and replacing all the partial derivatives with covariant derivatives and the Minkowski metric with the general metric of the background spacetime. This fully takes into account gravitational interactions. Now, in standard QFT, QFT describes fields, you quantize them, and then that lets you describe particles. And if you have ever wondered why this works, so what particles really are, so once you get beyond the understanding that particles are little red and blue billiard balls, you realize that what we're doing here is exploiting space-time symmetries. So what particles really are, these are quantized representations of the Lorentz group. So that is why they have energies and momenta, because they correspond to the space-time symmetries. And of course, that is a problem. So once you go from Minkowski to some general spacetime, we don't have Poincare invariance anymore. So what do you even expect to mean by the question how to describe particles in this spacetime? And that's at the base of the problem, what you want to describe with QFT and curved spacetime. You should realize that even asking the very question, what is QFT? What do we describe? How do we describe scatterings of particles? Yeah, you first need to define what kind of objects you're talking about. So let's illustrate that with the case of a free scalar field. Yeah, so by free, I just mean that I have a mass term. And in Minkowski space, the D'Alembert operator is calculated with respect to the Minkowski metric. So then, of course, you know the solution of that, the Calan-Gordon equation. So we have positive and negative frequency modes. Yeah, so classically, this just solves the Calan-Gordon equation. Then you quantize it, and then these coefficients here become operators. Yeah, and that's the classic way of how you introduce to QFT, where you can see sort of very nicely some wave-particle duality, because you have these plane wave factors that satisfy the wave equation, and you have operators that manifestly point to the particle picture, because this is the Fock space construction where you sort of diagonalize your theory, and you have states with definite energies, yeah, quantized states. Okay, and then you also know that you define the vacuum as the state of lowest energy. And that means that this is the state that is annihilated by all these annihilation operators. And while you correspondingly have one particle states by acting with a creation operator on the vacuum. Yeah, so that's what I mean by this statement here. Yeah, this construction is Lorentz invariant. The definition of the vacuum is Lorentz invariant. And this is what you really mean by a particle in QFT. Okay. So, crucially, what happens here is that you need to distinguish the positive and negative frequency modes. Yeah, this is how you know where to put the A and the A dagger. Yeah, but how do you distinguish positive frequency modes? How do you know what a positive frequency is? Yeah, well, you basically need a symmetry. In Minkowski space, it's obvious. The corresponding thing, I mean, it's the symmetry that is related to the conservation of energy. Yeah, so in GR, you would say that, well, you have something like globally conserved energy if there is a time-like killing vector. Yeah, so you need a corresponding space-time symmetry. So you need a time-like killing vector to distinguish So that means that if I call this this thing here some mode function uk, yeah, generally speaking, how do I know that this is the positive frequency mode? Well, I have to act with my killing vector on this, which in Minkowski space is just the time derivative. I'm just seeing that I'm mixing up my annotation here, which is not good. Yeah, where the frequency is positive. Yeah, so this is really how you can be sure that you talk about positive and negative frequencies, how to assign that. And that's absolutely crucial in the discussion. Okay, so this tells you again already that you have a problem in general. Yeah, so let's try to discuss the same thing in general. Yeah, we want to follow the same steps. So then we have the Klein-Gordon equation, but now we should calculate the D'Alembert operator with respect to some arbitrary background metric. Yeah, we can again do a Fourier composition, Fourier transformation. With respect to the spatial parts, yeah, so then we get the Fourier components as functions of time. And then we can identify some complete set of solutions to this equation here in Fourier space and write this in terms of this complete set of solutions, U. But now, for a general background metric, this choice here is no longer unique. Yeah, so for the Minkowski case, I have plane wave solutions. Yeah, and that's the ones that give me definite modes of positive or negative frequency. Yeah, of course, I can always, mathematically, describe all solutions with a different set of basis functions, but they will mix positive and negative frequencies. Yeah, so in that sense, it's unique for the Minkowski case, but no longer here. So I don't know whether I should use basis functions u or v. Yeah, then I would introduce some different basis functions v instead of u, and correspondingly creation and annihilation operators b rather than a. Okay, I still know something. Yeah, if I want to make sure that the basis functions that I use here, in order to fully construct all solutions to the Klein-Gordon equation, they should be orthonormal. Yeah, I can always make sure that this is the case. So that means that I can write my basis functions v as a linear combination of the basis functions u. Yeah, just because it's a complete set of basis functions. Okay, now you can plug this decomposition in here, invert it to solve for a as a function of b, or the other way around, and you find the following. As expected, I can also express my creation and annihilation operators in the v basis in terms of creation and annihilation operators in the u basis. So these things here, alpha and beta, are referred to as Bogoliubov coefficients. And what is the meaning of these things? Yeah, to understand that, I can, for example, create a vacuum state with respect to this decomposition. means my vacuum state annihilates all the annihilation operators annihilate the vacuum state, but I should actually specify that this is the vacuum state with respect to U. Okay. But then, of course, in the vacuum, you don't measure any particles. Yeah? The number of particles is 0. This is the number operator. But if instead you choose the same state and ask what is the number of particles that an observer would see who chooses a parameterization V, yeah, you just plug this in here. So that observer would of course measure BKB. Yeah, you plug in this decomposition in terms of A's. Yeah, and then you quickly see that, B is actually a linear combination of A and A dagger. B dagger is a linear combination of A and A dagger. Yeah, so you get 4 terms in total. 2 of them are killed immediately because you have an A here to the right or an A dagger to the left. Yeah, but there are 2 terms that are not killed, yeah, because they come in the form of A dagger. Yeah, and then you have to use the commutation relations, so you get a non-zero contribution. And this is simply B squared, where we use the normalization of the vacuum. Yeah, so this is the intuitive meaning of these Bogoliubov coefficients. Yeah, so what this describes is basically the creation of particles. Yeah, with respect to one choice of basis functions, you prepare a vacuum state. But with respect to another choice of basis functions, this state is not a vacuum. Yeah, and that's exactly what happens in cases that you are familiar with. Yeah, it's the case in Hawking radiation, Unruh radiation, in the early universe during particle production during inflation. Yeah, so for Unruh, for example, the 2 basis functions would be here. I mean, for the Unruh effect, we are in Minkowski space. Yeah, so these would be the ordinary plane wave solutions. And these here are the basis functions that the accelerated observer would use. So the accelerated observer would use plane wave solutions in the frame of the accelerated observer. Yeah, and then if you do the math, you find a production that looks like a thermal spectrum. In the early universe explication, what typically happens is that, and that's also what we're interested in here, you have this kind of basic equation, Klein-Gordon equation, an equation of motion. Yeah, you start with locally just Minkowski space, and then you take that as an ansatz to parameterize your solutions at some initial time t0. Yeah, while for the V's, you take the full solution at later times. Yeah, and then you decompose into positive and negative frequencies, and you get a beta, a Bogoliubov coefficient that is a function of time. Yeah, so as the universe expands, you produce particles. Okay, so just to give you a toy model example, now we can consider the case of just 2 scalar fields. Yeah, so we can never switch off GR, and then we have a scalar field phi and a scalar field psi. sorry, chi. This should be our dark matter particle. So this is really just a free scalar field. No interactions whatsoever with the heat bath. And this here takes the role of the inflaton. Yeah, so we are using times where the inflaton dominates the overall energy density of the universe, but describe the end of the inflation, so the reheating part. So this is here we need to assume some potential in order to drive inflation. So what you get from this picture then, if you plot the total energy density of the inflaton, we have some potential energy, and this is basically everything that dominates the potential during the phase where we are still in the inflationary phase. So this is the slow roll part. But then at the end of inflation, reheating starts. Yeah, so that means that the inflaton starts to oscillate in the potential in the around the minimum. Yeah, so then the potential energy goes down like that, and at the same time the field starts to pick up kinetic energy. So initially we are in somewhere here, we are still in the slow roll regime, and then at some point the Hubble friction becomes less relevant, you roll down and start to quickly oscillate here, and that's this part of the evolution. Yeah, so that's the kind of scenario we want to consider. And yeah, I think I don't really want to give all the details now because then we run out of time. So in this example, what you're basically doing is well, for simplicity, you choose coordinate, so conformal time rather than the coordinate time. You have a simple FRW ansatz, and also you introduce rescaled fields, and basically use a Hamiltonian set of equations of motion. So then you have, in Fourier space, the Hamiltonian equations of motion, you can compute the compute the right hand side. You get differential equations, and you express the fields and the momenta in terms of a Fourier decomposition. Yeah, in this Fourier decomposition, the coefficients have the same role as the coefficients that I had here on the blackboard. Yeah, so these are these functions u and v. Yeah, and then you start with a initial state where you just have plane wave solutions at some time. Yeah, and the final state is the full solution S and V. You find a time-dependent Bogoliubov coefficient like that. Yeah, so the actual calculation is quite complicated. So I just want to say that the starting point is relatively straightforward, but then you get a coupled system of the equations, namely the Hamiltonian equations of motion, and that is pretty difficult to solve. Yeah, however, there is a limit in which you can solve it exactly. And this is the limit where you have large momenta. Yeah, so momenta larger than the scale of the Hubble scale at the end of inflation, which is roughly the it's the mass scale of the inflaton. And there you find a scaling that goes like this. You know, the point is that you can actually, I put a reference in the notes. Yeah, so they managed to do this calculation in this limit here exactly. Yeah, so even the prefactor you can actually compute by solving this system of equations. But then there's a more complicated case where you have small modes. And well, first of all, let's put the massless case, massless dark matter case. Then you have a scaling that goes like k to the minus 6. And if you have something in between, they find a scaling of k to minus 3. Yeah, so again, this one is exact. This is with a somewhat uncertain overall factor that they managed to do this numerically, but not analytically, while this one can be done analytically. Okay, so what does that tell us? How should we interpret this? This is a pretty abstract concept. Yeah, you would believe that, it's hard to point to any mistakes, but it's still difficult to get an intuition of this. Now, there's a completely different way of understanding the same process. Yeah, and that is a perturbative picture. So we can write the metric as just a perturbation of the Minkowski metric, yeah, as in Yvonne's lectures on perturbations. And of course, if you plug that into the action here, yeah, this linearizes everything. Yeah, so then the dominant contribution is, well, here just the Minkowski term times the Minkowski free space expressions for the scalar fields. Yeah, but linear in H, there will be a coupling between the H mu, the graviton if you wish, and these terms. Yeah, this is the coupling between gravity and the matter parts. So we have an action it's basically kinetic terms for the graviton. So this is the Fierz-Pauli Lagrangian. The Minkowski Lagrangians for the scalar fields, and the coupling of the graviton to the stress energy tensors of the scalar fields. Yeah, now, the way this is formulated, we suddenly describe a theory in Minkowski space. Yeah, so we have a theory in Minkowski space with two scalar fields and a spin 2 field. Yeah, so then we would say that, oh well, of course we know how to describe dark matter production, namely through freeze-in, as we've done it all along. Yeah, we have this field initially, there's a coupling to the graviton, and that will produce, in a Boltzmann way, our dark matter field. So there's only an S channel contribution. And then you really do literally what we did for the freeze-in case, just that this process is so simple that you can actually directly solve the Boltzmann equation at the phase space level. And what you find is the same scaling as here. And in fact, not only the same scaling, but analytically exactly the same prefactor. Yeah, so we have two completely different pictures, but they describe the same physical process. So, take home is that these are very complementary viewpoints. And you basically have to specify which regime you're in. Yeah, in this regime here, yeah, that's the perturbative regime, you get the same result, so you can use both prescriptions. This one is typically much, much easier. Yeah, so why do I call this perturbative regime? Well, because here the momenta of the dark matter particles that we produce from the process to the left are always larger than the mass of the inflaton. Yeah, and of course, I mean, by energy conservation, that's what you must have. Yeah, you have two inflatons annihilating, so you get in the center of mass frame two momenta that are, well, at least the mass of the inflaton, yeah, plus some initial kinetic energy of the inflaton particles. You can never produce quanta here that have smaller energies than the mass here. Yeah? But apparently, the Bogoliubov approach gives us a contribution even in the other kinematic regime. Yeah? So this is a non-perturbative result. So there we must use the Bogoliubov approach. It's not possible to describe it with this kind of language. Okay, that's what I had to say. Thanks a lot for listening. Yeah.
For this perturbative production, you had to assume a specific potential in this process.
Sorry, I had to assume.
Like just the power of the distribution. Is it for any?
It's just from this Lagrangian.
Yes, but like you, for the inflaton, you have to assume a potential for the rate.
No. Oh, okay. So only indirectly. Yeah, so only indirectly in the sense that, I mean, the collision term is independent of the potential. Yeah. So where the potential enters is of course indirectly, because the potential specifies how much inflaton field I have at the end of inflation and how it oscillates during reheating. Yeah, so the number density of the incoming fields, if you wish, in this language, the number density of the inflaton particles, this is determined by the potential of the inflaton. But what enters in the collision integral, the scattering amplitude, the matrix element, is independent of this.
Shouldn't enter like a stress energy tensor?
Yes. Okay, so let's see. So what's happening? Okay, so yes and no. Yeah, so yes, absolutely. So it happens in a stress energy tensor. So this is where your mass and so your energy density and your pressure enter. Yeah, but of course, like for a scalar field, and you basically have the kinetic term, and then plus the potential term, and the pressure is like this. Yeah, so this is just quadratic in the fields and close to the minimum, since we are oscillating around the minimum. This is also just quadratic in the fields. So what enters is really just the mass, so the curvature of the minimum to the level to which we are computing this here. So in this sense, it doesn't enter, but it enters indirectly, as I said, in the number densities which multiply the overall rates. Yeah? Other question? Yeah.
Just out of curiosity, does this gravitational production get any sort of constraint at all?
Yes. Very good question. Yeah. So there's a big problem that you should be moderately aware of after the cosmology lectures again. Yeah, because here we produce dark matter in a way that is completely decoupled from the thermal bath. Yeah, so, and I told you that we need dark matter in order to describe density perturbations. Yeah, now the important part about the density perturbations in standard cosmology is that they are adiabatic. If you produce something non-thermally, this will lead to non-adiabatic density perturbations. And those are very strongly constrained. Yeah, so in particular, for very light dark matter particles produced this way, this is basically constrained or even excluded by the CMB, because you would see this in terms of non-adiabatic fluctuations. Yeah, so you need to make sure to somehow get around this, and ways to get around this is like either self-interactions that these light scalar fields thermalize, or somehow with heavy fields in the early universe. Yeah, I mean, you can be rather agnostic about what happens, but you cannot, for all of the mass range, allow really zero interactions, because that would be excluded later on.